Good day, everyone. So this is a new lecture series on numerical methods 1. And in this lecture, we'll be considering the overview of numerical methods and their applications. And some of the numerical methods considered in this lecture series are the analysis of numerical methods for ordinary differential equations, for which we look up methods for solving initial value problems, such as the Euler's method, the improved Euler's method, and the Runge-Kutta methods. And then we'll also look up the boundary value problems and the characteristic value problems, where we'll look up the finite difference method for the boundary value problems, the shooting methods, then the eigenvalue problems, where we'll consider the power method and the inverse iteration method. And then we'll also move on to look up spline functions, where we'll look up the linear spline, quadratic spline, cubic spline, although cubic spline finds wide application. As we'll uncover shortly, the basis spline and the Beiser splines. And also, we'll look up nonlinear equations. We'll consider the bisection method, the Newton-Raphson method, the secant method, fixed point iteration, and Muller's method. And then we move on to look up the approximation of functions, where we'll consider the polynomial approximation, where we'll talk about the Taylor series, Chebyshev polynomials, and the Lagrange interpolation. Then we'll also consider the piecewise polynomial approximation, such as the spline functions. And then the least square approximation, Chebyshev approximation, the min-max approximation. And also numerical methods for the solution of partial differential equations. We also look up the classification of partial differential equations, the elliptic, parabolic, and hyperbolic partial differential equations. And then we also look up methods for solving partial differential equations, the likes of the finite difference method and the finite element method. And we'll also look up numerical integration, where we'll consider the trapezoidal rule, Simpson's rule, Gaussian quadrature, composite numerical integration methods, and the adaptive quadrature integration, numerical integration techniques. And while we look up these topics, we'll also look up how we could apply some of the standard software libraries, the likes of MATLAB and Python in modeling and simulating some of these problems. Our major emphasis will be on looking at the application domains where these numerical methods apply. Coming from the electrical and electronics engineering background, so we'll be considering applications in communication engineering in this series, control engineering, electronics engineering, and power systems, machines, and drives. And here we have some of the selected applications, though this is not exhaustive, but just a few applications pulled up in these domains. I mean, the communication, electronics, control, and power systems, machines, and drives domain. And here we are able to pull up some applications where we are able to apply these numerical methods. So here we see that the ordinary differential equations, the ODEs, apply in communication engineering, engineering for modeling signal transmission and filtering systems, simulating signal propagation in communication channels, and also in analyzing the bit error rates in modulated signals over time. And in the electronic engineering field, they are used for solving circuit equations for RLC circuits to predict transient and steady state responses, and also for analyzing transient behavior in RLC circuits. Then we also use them for simulating charge discharge cycles in capacitors and inductors. And in control engineering, the ODEs are used for simulating control system dynamics, such as the proportional integral derivative controller responses. Also for designing control algorithms for dynamic systems like servo motors, and also for simulating transient responses of feedback control systems. While in power systems, machines, and drives, the ordinary differential equations are used for modeling and simulating transient responses in power systems, such as fault analysis and voltage stability, also for modeling and solving dynamic behavior in power systems, and the likes of transient stability analysis of power grids, and also for simulating load flow and generator dynamics, and also DC motor transient analysis. And the boundary value and characteristic value problems find applications in communication engineering for determining electromagnetic wave modes in waveguides and antennas, and also for analyzing propagation modes in transmission lines and waveguides. Then we also have an application here, which is the design of antennas based on the Eigen function or Eigen frequency analysis. And then in electronics engineering, they are used for solving boundary conditions in wave propagation within microstrip lines and waveguides, and also for solving waveguide boundary problems in microwave circuits. Then we also have the eigenvalue problems in vibration analysis in microelectromechanical systems and devices. And then in control engineering, the boundary value and characteristic value problems applies in stability analysis of control systems via the eigenvalues, and also for designing optimal controllers using eigenvalues for state space systems. Then in control engineering, we also use them for analyzing stability of control systems. While in power systems and machines and drives, they're used for analyzing load flow in transmission lines using the eigenvalue problems, solving boundary value problems for thermal conduction in cables. Then we also have the eigenvalue analysis of for the stability of electrical grids and the magnetic potential in machine status. And then the spline functions are used in communication engineering for signal interpolation and reconstruction in digital communication systems, and then for designing digital filters for noise reduction, and also for signal reconstruction for sample data in communication systems. While in electronics, they're used for designing and reconstructing signals in digital signal processors, signal reconstruction in analog to digital and digital to analog converters, and for smoothing noisy signals from sensors in embedded systems. Then in control engineering, spline functions are used for smoothing control signals, for better performance and noise reduction, also for interpolating noisy sensor data in feedback loops, and also for reconstructing trajectories in path planning systems. While in power systems, machines, and drives, they are used for interpolating missing load or generation data in power system simulations, for interpolating load profiles, for power generation planning, or better say optimal power generation planning, and for smoothing energy consumption data for predictive analytics. Then we also have the torque speed interpolation. While the nonlinear equations are used for modeling and optimizing nonlinear signal propagation in communication engineering, and also for solving nonlinear equations for signal demodulation and analyzing nonlinear distortion in amplifier. Well, are just few applications mentioned. And for electronics, they are used for determining the operating point of nonlinear devices, such as the metal oxide field effect transistors and bipolar junction transistors, the MOSFETs and BJTs, and also for finding bias points in transistor circuits, such as the MOSFETs and BJTs, and analyzing the nonlinear current voltage characteristics of diodes. Then, in control engineering, the nonlinear equations are used for solving nonlinear control system equations for stability analysis, and also for designing nonlinear controllers using the root finding algorithms, and for solving equations for robotic arm kinematics. And in power systems, machines, and drives, nonlinear equations are used for power flow analysis using the Newton-Raphson methods, for instance. Also for finding the operating point of power electronic converters, and for solving load flow equations in electrical grids. And they're also used for the permanent magnet synchronous motor saturation analysis when it comes to machine studies. Then the approximation of functions in communication engineering are used for signal demodulation and reconstruction in communication systems, the likes of designing modulation and demodulation schemes, and also for approximating channel impulse responses for equalizers. And in electronics, they are used for the Chebyshev polynomials in designing filters and amplifiers. That is to design the Chebyshev filters for analog and digital circuits, for instance, and also approximating diode and transistor characteristics. And in control engineering, the approximation of functions are used for designing least squares based controllers to minimize errors in the system's output, and also for designing least squares filters for control signals, and approximating space models for complex systems. And in power systems, machines, and drives, they are used for estimating load demand curves and power generation profiles using polynomial approximation. Also for approximating power curves for renewable energy sources like solar and wind energies, and then for least square fitting of load demand curves and motor losses versus load. And the partial differential equations are also used in communication engineering for simulating electromagnetic wave propagation in free space and waveguides, and for solving the partial differential equations for antennas and waveguide design. Then in electronics, the partial differential equations are used for modeling heat dissipation in microelectronic circuits and thermal modeling of microprocessors and semiconductor devices, and also for analyzing electromagnetic wave propagation in circuits. Now, in control engineering, the partial differential equations are used for simulating distributed systems like thermal or fluid flow in control systems, and also for modeling heat distribution in robotic actuators, and also simulating fluid flow for hydraulic control systems. While in power systems, machines, and drives, the partial differential equations are used for solving heat diffusion in transformers and other power devices, also for solving heat conduction equations for transformer and cable design, and then for modeling power grid stability using the wave equations and heat conduction in motor windings. Now, the numerical integration is used in communication engineering for estimating power spectral densities of signals and also for calculating the signal energy. We also use the numerical integration method for calculating signal power and energy in communication systems, and also for evaluating the spectral energy distribution using the Fourier transforms. And in electronics, they are used for computing energy stored in capacitors and inductors over a given time period, and then also for estimating the energy of signals in the time domain analysis and computing power dissipated in resistors using the definite integrals. And in control engineering, the numerical integration method is used for numerical integration for simulating continuous time systems, and also for estimating area under a control signal for energy analysis, and also for computing the total torque generated in mechanical systems. While in power systems, machines, and drives, the numerical integration method, or methods rather, are used for calculating energy delivered over time in power systems, and also for evaluating power loss in transmission lines, for instance, energy calculation in induction machines, the flux linkage in permanent magnet synchronous machines, torque computation in switch reluctance motors, and loss estimation in drives. But these are just a few, and the list is endless. While in this series, we try to tailor the application of these numerical methods in addressing problems in electrical and electronics engineering, the idea is that these techniques or methods could be applied in other engineering fields and even in the sciences. And we are hopeful that the series becomes a handy tool for both researchers and postgraduate students. So in subsequent lectures, we'll be diving into the numerical methods, and as we progress, we appreciate your comments and suggestions for possible improvement. Thank you.